It is a truly wonderful pleasure to have Denis Bandurin here as our first speaker for the fall season. Denis, thank you so much for accepting the invitation. And as a brief background, let me tell you a little bit about Denis. So Denis got his PhD at the from the University of Manchester in 2017 in the UK. Then afterwards, he was a Lever Hulme Early Career Fellow of the University of Manchester. And afterwards, he moved to MIT in US, where he was a Pappalardo Fellow, working on different aspects of two-dimensional materials. And since 2022, he's an assistant professor at the National University of Singapore. Denis has been working in some of the most exciting directions in two-dimensional materials, and in particular in low-dimensional physics, quantum transport, radiation-driven phenomena, and many aspects of plasmonics. And just as a brief summary, he has been working on really fascinating topics in hydrodynamic of electron transport and viscous Hall effect in graphene, on physical drag in graphene plasmonics, kinematics and Hall electron viscosities. And he has been working on the development of novel principles for terahertz detection. And today, Denis is going to tell us about light-matter interaction in the flatland, recent advances, and novel applications. So with this, Denis, thank you so much for accepting the invitation. The floor is yours, and we look forward to your talk.
Thank you very much, Jose, and many thanks for the organizers for inviting me to give this seminar. It's a great pleasure, and in particular to see you, Jose. Yeah, I know Jose for a long time. We were in the same time during the PhD in this Marie Curie program. Had lots of fun on different conferences. I learned a lot from Jose. Yeah, it's nice to catch up in this kind of format. Thanks a lot for introduction. And the goal of my today's presentation is to convince you that despite extensive studies of two-dimensional materials, the flatland still brings us very interesting and sometimes, quite counterintuitive effects that not only can be important from the fundamental view, but also these effects may find some interesting applications in technology. So as you can see from this very strange but sort of mysterious image generated by AI, we will talk a lot about graphene plasmonics. I was thinking a lot how to start the presentation until I found this website which generates AI images. I mean, I'm not sure if you can see plasmonics here, but you can definitely see graphene, and I think it's a good picture for the beginning of the presentation. All right, so first of all, this is the most important slide of my today's presentation is my colleagues. In particular, I'm going to tell you a few stories which were done in collaboration with different people. In particular, the groups of Dmitry Basov, Leonid Leviatov, Michael Fogler, Pablo Yarila Herrero, Gregory Goldsman, Dmitry Svintsov, and Sergei Ganichev. So, and they're wonderful students and postdocs. Right. So to begin with, let me remind you that light-matter interaction in low-dimensional systems often involves the excitations of polaritons that are hybrid modes between collective excitations of different quasi-particles in your material and photons. And so depending on the material's properties, these polaritons can be of very different kinds. For instance, if your material is a semiconductor, it can host the so-called exciton polaritons, which are hybrid mode between the excitons and photons. It can host, if your material is an insulator, a specific type of an insulator, such as hexagonal boron nitride with some fancy anisotropic properties, it can support the propagation of phonon polaritons. If your material is a magnetic thing, then you can have magnon polaritons. And recently, there has been a lot of work being done in the field of Cooper pair polaritons, where people are trying to explore the collective excitations of superconductors together with light. So many of these modes may reveal very new and interesting physics, but they also can give rise to practical technology. So today we will be talking about the plasmon polaritons that represent coupled self-sustained oscillations of electron density and the associated electromagnetic fields. So plasmon polaritons are typically hosted by high conductivity materials, metallic systems, and in 2 dimensions, they have a square root of 2 dispersion. If you were to visualize these modes, you should think about kind of ripples on the surface of a shell of wave. A particularly useful and certainly interesting material for the field of plasmonics is graphene. And the reason being is that it supports the propagation of long-lived electrically tunable plasmons, and those plasmons mostly live in the mid and far infrared frequency domains. These plasmons are characterized by very large compression ratios, which is the ratio between the plasmon polariton modes in this material and the the wavelengths of the incident radiation that excites them. So in graphene, these modes can be compressed by a factor of 100. They're also long-lived and can propagate micrometer scales without scattering. And by applying a gate voltage to your graphene device, by changing the carrier density, you can tune the dispersion of these modes because you will be altering the velocities of those modes. So the interesting thing, of course, is graphene plasmons, unlike plasmons in systems in other two-dimensional systems, for instance, gallium arsenide heterostructures, they kind of live on the surface of a very thin material, and therefore they are kind of exposed to the surface, and therefore there are special tricks how you can literally see and observe them by means of so-called scattering type scanning near field optical microscopy technique. So the technique is kind of illustrated on this image. It's nothing but an atomic force microscope tip, which is illuminated by the laser light, and using some special demodulation tricks, one can capture the local distribution of the field intensity and thus literally see and visualize the propagation of plasmons. So this is the typical picture of such measurements produced by Dmitry Basov's group back in 2018. You can see that there is this gold particle from which the plasmons propagate for long distances, micrometer scale distances in this case. And what's importantly, by using this technique, you can reconstruct the optical conductivity of your material and study it as a function of different properties. For instance, the electric environment, gate voltage, carrier density, substrates, and so on and so forth. So the way you usually do it is you would make the snapshot of the plasmons, you would measure its wavelength. From this, you would reconstruct the plasmon wave number, and then knowing the frequency of your excitation, you would put a point on your dispersion. And then you would do it for other frequencies of your excitations, and thus you can reconstruct the full dispersion using such measurements. And the reason why this is very important and useful technique is that by studying it, you can look for very interesting fundamental effects. For instance, using such method, by studying the plasmon polaritons, the group of Frank Coppens a few years ago revealed very important interaction-driven quantum corrections to the electronic properties of graphene simply by studying the propagation of those plasmon polariton modes as a function of the distance to the dielectric, where you can tune the importance of those effects. So today we will talk about 3 pretty short plasmonic stories. 2 fundamental stories and 1 applied. And I suggest we start discussing with probably the simplest story, applied story, and then gradually transition to the more kind of intricate and more complex fundamental stories. Okay, so the first story is related to the resonant detection of sub-terahertz and terahertz radiation using graphene plasmons. First of all, I would like to remind you that terahertz radiation is a very important yet technologically challenging frequency domain when it comes to observational astronomy, security inspection, navigation of autonomous vehicles, quality control systems, and most importantly for beyond 5G communications. And as most of you probably know, that this frequency domain is too fast for electronics and too slow for optics. That's why it's pretty challenging to be addressed by conventional methods. However, it turns out that this frequency domain is sort of very good for graphene plasmons, because plasmons propagate faster than electrons and slower than photons. So it's kind of in the intermediate regime. So let me show you like a simple example how you can take advantage of graphene plasmons to build practical terahertz devices. You remember I showed you these 2 pictures before, which is the plasmon polariton dispersion in graphene and the snapshot of the real plasmons propagating through the flake, through the channel. If you notice, once again here, plasmons are launched by these gold contacts. And the reason is pretty obvious. In order to launch plasmonic modes, one has to overcome a momentum mismatch between the incident photons, which has almost 0 momentum, and plasmons with finite momentum. And usually sharp metal objects such as this gold contact or a tip or some small gold particle can act as a near-field antennas, enabling to produce harmonics of the scattered light with needed wave numbers that can couple to collective polariton modes and that therefore excites them. So what we decided to try is to add another contact opposite to the first one in order to create sort of a resonant cavity for this mode. So this kind of picture, which is taken for the from the near field image, is just for illustration purposes. But what you end up with is a conventional sort of two-terminal graphene device, which you usually use for transport experiments. I'm showing you here. So the typical picture of our device, we had like a long graphene or bilayer graphene channel encapsulated between hexagonal boron nitride, which, as some of you know, provides the best quality for graphene's electronic system. And then we have these two contacts on the left and right side of our device. I hope you can see my cursor. If not, just let me know. And then we took this device and connected it to a broadband antenna, which I'm showing you here, and then we exposed it to the terahertz radiation. So what I will be showing you in the next pictures is the photovoltage which is built up across this graphene channel when we expose it to terahertz radiation. So this is the typical picture of such a photoresponse. Well, I'm showing you in the units of responsivity, which is the voltage built up between the source and drain channel divided by the power of incident radiation. So if you were to look at carefully at the responsivity versus the gate voltage which you apply to your graphene channel to tune the carrier density, you will see that the photovoltage experiences those dips and peaks or sort of oscillations as a function of the carrier density, which is controlled by this gate voltage. And you can see those kind of pretty much regular oscillations for electron doped sites and some wiggles for the holes doped site. We think we understand it now. But what's importantly is that these oscillations are nothing but different resonant modes of the cavity, which you tune by the gate voltage. So if you were to sketch it over here, you will see that you can have standing plasmonic waves between the source and drain channel. And the way to prove that those oscillations correspond to those waves is, of course, to change the frequency of your excitation and to plot these oscillations as a function of inverse gate voltage, because that's how your velocity of well, in this case is the group velocity of your plasmon changes with the gate voltage. So if you see the regular oscillations in these coordinates, this means that you are exciting plasmonic modes. So and this is the illustration of the third mode, which is the which is this pi over 2L 2 times 3 plus 1 mode hosting between the source and drain channel of your field effect transistor. So in this case, you sort of create an interferometer for your plasmons, and if you were to do an analogy with the free space optical system, this would mean you would sort of change the distance between your mirrors. But here you are changing the gate voltage and tuning your devices between different modes. As for instance, like here, I'm showing you a couple of different modes, again, controlled by the gate voltage. So, if you have this resonant photoresponse, first of all, the first thing which you can have is the resonant enhancement of the responsivity of your detection. So once your electron fluid is shaken inside, you can expect the enhancement of the photovoltage, which is built up there. But the second thing is you can use this property for the on-chip terahertz interferometer or spectrometer, where you change the carrier density and then go through a series of peaks, and then you can reconstruct the frequency components in your incident radiation. So this is kind of the basic idea of this type of devices. But in addition to sort of applied direction, these kind of devices are also useful from the fundamental point of view. For instance, you can replace your graphene channel with any material which would support plasmon polaritons here, and see and study the properties of these collective modes in where other techniques are arduous. For instance, at very low temperatures or in the presence of magnetic field. And in this case, we try to integrate in this material, in this sort of devices, bilayer graphene hexagonal boron nitride Morse superlattice. And this is the typical resistance of this kind of devices. Those of you who are familiar with the transport in superlattices will recognize the appearance of the secondary neutrality points in these devices. And if you look now at the photoresponse in these devices, you will see not only you have the resonances close to the main neutrality point, which correspond to the regular bilayer plasmons, but then you also see the resonances close to the secondary Dirac point, and these modes and the photovoltage in these modes have opposite direction, which means that they are hosted by the quasi-particles of opposite sign, and in this case they are hosted by the mini bands formed as a result of the superlattice formation between the lattices of boron nitride and bilayer graphene. So now we're expanding these studies to the magnetic field to hunt for the plasmons which are hosted by these Hofstadter mini bands in the spectrum of graphene HBN superlattices in the presence of magnetic field. All right, with this I would like you to take home two messages regarding the first story, that graphene plasmons can be used for resonant detection of terahertz radiations, and you can use these sort of devices to reveal new physics, for instance mini band plasmons in graphene HBN superlattices. So usually these plasmons are very hard to observe, these mini band plasmons are very hard to observe by other techniques. There were experiments in the near field studies, however there were no plasmonic modes observed at terahertz frequencies there. In our techniques we managed to see them by this very simple setting without involving very complicated scattering techniques. And also, who knows, maybe you can use this for real practical applications, because already the responsivity of our devices is pretty strong. Now I would like to change gears and transition to the second plasmonic story that we've done in the group of Dmitry Basov at Columbia University. During my stay at MIT, I would travel to Dmitry's lab in New York with the devices that we produced to measure very interesting effects related to Fizeau drag, which I'm going to tell you in the following section. So in modern low-frequency photonics, there is a very important yet technological problem, namely the quest for optical non-reciprocity. The optical non-reciprocity is a crucial effect for optical isolators and circulators, and usually it's routinely achieved via different magneto-optical materials, where the time reversal symmetry is broken by applying a magnetic field, or by means of different nice and fancy techniques and ideas from the topological photonics. In addition to these approaches, it is scarcely realized that the non-reciprocity can also be achieved in plasmonic systems. So the idea is that if you act on an electronic component of the polaritons by the direct current, the optical component should adjust accordingly. So now let's have a look again at this dispersion of plasmons, which I showed you before. At zero velocity, when you don't act on your electronic component, you have a symmetric square root of Q dispersion for positive and negative wave vectors. However, if you now apply some kind of DC current flowing through your device, you will see that plasmon polaritons propagating and counter-propagating to the charge carriers now will have very different dispersions or different frequencies for fixed wave numbers. In graphene, these phenomenon, this effect was predicted theoretically quite a long time ago. However, despite these predictions, this effect has not been tested in solid-state plasmonic devices, and there were a few reasons which I'll tell you later why this was challenging so far. But before that, let me also mention that this effect is very similar to the celebrated Fizeau drag effect discovered in the 19th century, in which the flow of water in which the flow of water was found to alter the light velocity. And in our case, it's the electron fluid which was supposed to drag light in the form of plasmon polaritons and alter its dispersion. So first we tried to catch this effect, this physo-drag effect in the antenna coupled devices, quite a few, like 4 or 5 years ago, with the same colleagues with whom we did this resonant terahertz detection. However, we realized that, in these sort of devices, in these resonant cavities, we are dealing with standing waves, and therefore if we introduce some kind of directional motion of charge carriers, whatever will happen with the forward moving wave will be cancelled out by the backward moving wave, and therefore all these effects will be mitigated in the standing wave configuration unless we're dealing with some corrections to it. And the natural solution was, of course, to use the scanning near-field optical microscopy technique. And with the group of Dmitry Basov at Columbia University, we attempted to visualize the propagating plasmons in the presence of current flow in their, very unique cryogenic SNOM machine. So this is the typical schematic of our experiment. Infrared light is incident on this gold antenna. You remember I told you before that if you have this gold or sharp particle or sharp contact, you will have plasmon polaritons exciting and propagating inside the channel. And then you can approach it with the tip of atomic force microscopy from this SNOM technique and use it as a detector to outcouple light and then literally visualize and make a snapshot of the propagating wave. Then what you have to do, you have to supply a pretty strong DC current and record the dispersion for the plasmons propagate, or record the response of the plasmon wavelengths for the plasmons propagating along the direction of the current flow and the opposite direction. And so to do this experiment, we needed to produce very high quality graphene devices, which would first support the propagation of those plasmonic modes for a very long period, but also these devices should have very low resistance contacts so that the devices can sustain very large current densities, and also these contacts should have very low resistance to work as heat sink for the temperature which is built up inside graphene channel when we supply extremely high current densities. And also these devices should be assembled on thick gate dielectrics to mitigate all the self-gating effects. So on the way, we burned quite a few devices, maybe a dozen of devices, until we learned how to produce them. In this case, the credit goes to my student Isabel Finney, with whom we produced those devices. And together with a very talented student from Dmitry Basov's group, Yinan Don, we recorded the, we eventually managed to record the plasmon polariton fields when for 0 and very strong DC current. So in this picture, I'm showing you the main result of this measurement. So the black curve is the plasmon polariton propagating in the channel at 0 DC current, and the blue curve corresponds to the data taken at very large current density passed through our device, almost a milliamp per micron. It's enormous current density, yet we still saw nice plasmonic fringes with a certainly reduced amplitude, but this was enough to infer the wavelengths and to look and to hunt for this shift of the plasmon polariton wavelengths as a function of current density. We did this experiment for many current densities and for different gate voltages, and now let's look at the quantified physo shift, which is the relative change of the plasmon wavelengths as a function of bias current, measured, in this case, measured for electrons. So here I'm showing you the delta lambda over lambda in percent as a function of current density that we pass in our devices, or you can relate this current density to the sort of drift velocity expressed in units of Fermi velocity. So we are talking about 10% of the Fermi velocity here. And as you can see, as you can see, there is a striking thing, like when the charge carriers counter-propagate the plasmon polaritons, the effect is pretty strong, while when they counter-propagate, the effect is, it starts, but then it kind of deflects the opposite direction. So graphene is a very important material for this kind of experiments, because now what you can do, you can test this if something which you are doing is correct or not. You can change the type of charge carriers to indeed test if it's the counter-propagation of charge carriers with the current flow which matters or not. So we gated our device with holes now, and we saw again absolutely the same phenomena. When the charge carriers, in this case holes, counter-propagate the polaritons, then the phasor shift is changing, is growing, while when they counter-propagate, the phasor shift is kind of small. And if you were to deal with the Galilean invariant system, such as, for instance, I don't know, system with a parabolic dispersion, say gallium arsenide at small carrier densities, small energies, you would see that you should be able to see a phasor shift for both positive and negative currents, and this effect should be symmetric with respect to the current direction. This was not definitely the case in our study until we realized that in fact in graphene, because if you account for complex optical conductivity of graphene, and in particular, which takes into account the linear dispersion, you will see that it's not only the first order phasor shift that is important in this kind of study, but also the second order, which is proportional to the velocity squared. So they happen to be of comparable amplitude, and that's why you have the deflection of the curve here. As you can see, the black solid lines I'm showing you here is the result of this sort of calculations. And for these calculations, we use the realistic drag term, as we call it for brevity, which is nothing but the ratio between the frequency of incident radiation and the electron scattering rate. If you plug the numbers, you'll get this dependence, which agrees well with our experiment. Now you can also look for the dispersion. So because before, if you remember, I was always showing you the this kind of square root of oh, okay, I did something wrong, square root of 2 dispersion, but in fact in graphene deposited on hexagonal boron nitride, the square root of Q dispersion, square root of 2 dispersion is modified by the presence of the phonon polariton mode at this 890 inverse centimeters. And now, like if you look at this dispersion, you will see that indeed for quasi-particles counter-propagating the flow, the dispersion is changed drastically, while if we're talking about the co-propagation of quasi-particles in the plasmon polaritons, there is practically no effect here. All right, so with that, I would like to conclude with the second part of my story. And I would like you to take home 2 messages: that electron fluids can drag plasmon polaritons, or you can think about them dragging light in the form of plasmon polaritons. That's why making this effect very similar to the phasor shift discovered in the 19th century. And the second message is that this drag is kind of described by the quasi-relativistic laws. But what I mean by that is that it doesn't follow the Galilean invariant, the Galilean transformation, as I showed you here, right? So the Galilean invariance would give you this linear, larger sloped, symmetric dispersion, symmetric change of the phasor shift. And now, as an outlook, now it's very interesting because our devices can sustain very large current densities. It's very interesting to hunt for different instabilities and maybe look for some kind of isolators or mid-infrared circulators, built on chip through this kind of ideology. Right. So now I think I'm transitioning to the last, again, fundamental part of my story that is again related to plasmonic effects in graphene, but in this case these effects are happening in the presence of magnetic field. Let's go back again to the same square root of Q dispersion we discussed previously, and look what happens if you apply a finite magnetic field. So most of you know that the magnetic field, when the magnetic field acts on the plasmon dispersion, it gaps out the bulk plasmon dispersion at 0Q, so that no plasmons can exist below this frequency, so that the bulk magnetoplasmons should only exist above the cyclotron resonance frequency. And of course, these effects were studied in graphene experimentally quite a few years ago with the advent of graphene, on like when the people learned how to produce large-scale graphene devices. And who would have thought that this kind of simple classical physics would give anything interesting, right? But we decided to study this effect just because we learned how to make this extremely clean and extremely high quality graphene devices by encapsulating them and by cooling them down to cryogenic temperatures where the scattering is mitigated. Scattering, say, with phonons, or with phonons is mitigated. So this is the setting of this device. And again, we wanted to look for the response of such devices to measure the photo response or photoconductivity of response to terahertz radiation again, but now in the presence of magnetic field. So out of curiosity, this experiment, we tried to catch those modes, but again, this was done in the far field geometry. We did it during my stay at Sergei Ganichev's lab in the University of Regensburg. So I'm showing you the device which I produced for this experiment. Is an encapsulated graphene device, but unlike many other devices studied so far, I intentionally didn't etch this device to define a specific shape, because usually etching introduces lots of defects on the graphene edges. But if the graphene has a natural edge, it's very natural to expect the improved quality of the scattering, the improved quality in general of your devices by reducing the scattering through the edges. But also you may notice that this device is a bit different than what you usually do for transport studies. In particular, it doesn't have those kind of ears which you made out of graphene to contact your gold leads. In our case, gold leads enter the graphene channel, and this was very important for this study. I'll show you later why. But now I just want you to pay attention to these small differences between conventional devices and this particular device. So now let's start with the experiment. Let's look at the experimental data. In this plot, I'm showing you a simple longitudinal resistance of doped graphene device as the doped graphene device as a function of magnetic field. So now we're talking about 3 × 10⁻¹² per centimeter squared of the carrier density. It's very metallic doped graphene, and we're looking at the magnetoresistance at very small magnetic fields. We're far from the quantum Hall regime. Quantum Hall in these devices at these carrier densities start a bit higher in the magnetic field, but this data is taken in the dark. So together with Sergei Ganichev's student, Erwin Mönch, we recorded not only the dark magnetoresistance, but we also switched on the 0.7 terahertz laser radiation of very high power. And we can see the appearance of this weird feature at 0.5 Tesla, this, the sort of increase of the resistance at 0.5 Tesla. And, the Shubnikov-Degas oscillations were still here, so the amplitude reduced a little bit, probably due to small electron heating induced by the terahertz radiation. But this feature appeared like very sharply, and it appeared around like 0.5 Tesla. So the first reaction when you see this kind of peaks in the presence of magnetic field and high frequency radiation is, okay, this must be the cyclotron resonance. What else can happen in the two-dimensional electron system subjected to the both electromagnetic field and the magnetic field? However, when we did the math, the numbers didn't match. The peak appeared at the magnetic field, which is exactly 2 times smaller than that needed for the cyclotron resonance to emerge, right? As you can see, like here, I'm showing you where the cyclotron resonance should take place, and here's where the feature was observed. In other words, we saw the feature at the second order cyclotron resonance, right? Or the first overtone of the cyclotron resonance, as we call it, to discriminate these two phenomena. I'll tell you why. So first of all, most of you probably know that the cyclotron, the second order cyclotron resonance is a very weak effect, usually happening together with the first order cyclotron resonance. So this effect is weak or even forbidden, both from the quantum points of view and from the classical point of view. From the quantum point of view, it's easy to understand. It's like, you cannot excite electrons, you cannot initiate intra-band transition between two Landau levels, right? And in the quantum and in the classical regime, the work which is done by the electromagnetic field on a particle at this frequency is precisely zero. So you need to have some kind of perturbation in your system ever to be able to ever see the feature at the second order cyclotron resonance. But in our case, we didn't see cyclotron resonance whatsoever at this carrier density. So I'm showing you it should happen somewhere here, but the effect happened at precisely the position of the second order effect. And we were puzzled for a while about this physics, because this effect, first of all, it occurred at all carrier densities. We checked the polarization dependencies there, which are also quite interesting. If we have time, we can chat about this. And this effect was linear in power, so which means it's not sort of instability related effect. And we were puzzled for quite a while about this weird feature, and the magneto resistance was quite strong. It's like 25-30% at this power. As we increased the power, the effect was just growing. So it was growing and growing while these Shubnikov gas oscillations were getting smaller and smaller. Although electron temperature was going up, the quantum effects were shrinking, but this feature at the second order was growing. And the resolution of this puzzle came from our colleague Dmitry Sventsov, who remembered that the magnetoplasma dispersion at high wave numbers can get split into a series of branches called Bernstein modes. So, of course, those modes are, of course, known from plasma physics, and they were also observed in certainly gallium arsenide base heterostructures. However, it seems that the key property of these Bernstein modes, in our opinion, right, like the key property, namely their ultra slow velocity close to the cyclotron resonance harmonics, and hence the diversion density of plasmonic states, was often somehow disregarded when you think about light-matter interaction in these kind of systems. If you have sort of a Van Hoff singularity in the plasmonic density of states, it's very natural to expect strong light-matter interaction and therefore giant light absorption. The only thing which your device has to do is to be able to absorb energy at these wave numbers, where the dispersion is flat, right? So in our case, the dispersion is flat somewhere here, and therefore, if your device can have an absorption at different Q spanning across this flat domain, you can get this strong absorption. However, previously, all experiments are either done in the far field settings where you have an absorption at zero momentum, or they're being done with the help of so-called grating, right? To select a specific wave number to excite a specific collective mode you want to excite in your system. But if you remember, in our device, I told you before, the gold leads the anti-graphene channel, and therefore can act as a scatter for the electromagnetic field, act as a near field antennas. Similarly to what I explained you before, when we look at this nice propagating plasmons close to the gold particle, to the gold contact, right? Now, we decided to test it, and Dima's student, Kirill Kapralov, modeled the near field magneto absorption of terahertz radiation facilitated by the scattering from this sharp gold leads immersed in graphene channel, and this is sort of the model which they used. The important part of this model is that it accounts for the absorption of electromagnetic radiation by the special harmonics of the electric near fields produced by this sharp contact. So this is the key difference as compared to the previous sort of ideas of absorption. well, it's not new. Definitely, if you calculate the near field response, you would do something like this. But now you also account for the collective modes sitting in your graphene channel, which have this flat dispersion. Let me show you the results of these calculations. So first of all, here's the loss function, or you can think about this as a sort of magnetoplasmon dispersion in the presence of magnetic field. You can see this is the leftovers from the magnetoplasmonic excitations in graphene, and now you have this series of branches which can only exist in very high quality devices and in the presence of very non-homogeneous fields close to well, such as those formed close to the sharp contacts in our case. So now let's have a look how these modes look if you were to visualize them using, for instance, using scanning near field optical microscopy technique. So at zero magnetic field, you would have those fringes propagating through your from your sharp gold contacts. At large frequencies, above the second order cyclotron resonance, which was supposed to happen somewhere here, above this gap, which I mentioned before. Again, nothing surprising happens. You have the, those waves, which have a little bit different wavelengths as compared to the zero magnetic field case. But now, as you come closer from the bottom of this gap and approach this dispersion from the bottom part, you will see that you will cap this dispersion in two parts, and now you will have a kind of a coexistence of the long and small and short wavelengths oscillations. And when you start lifting up the frequency even higher, when you come to this regime of the flat dispersion, these modes sort of coalesce, giving you a very strong absorption of electromagnetic energy. So let's have a look at the comparison between theory and experiment in our case. So theory is based on this idea. You can see the emergence of a strong feature at BCR over 2, where BCR is the magnetic field at which the cyclotron resonance should happen, and this is experiment. And the agreement is pretty remarkable. You can see this not only the absorption, you can also see the symmetry, this long tail, which again makes sense if you think about this, how you approach this the second order. The second order, but the gap at the second order cyclotron resonance. So the agreement was pretty good in between experiment and theory. But also we had like very interesting polarization data, which if some of you are interested, we can discuss. Anyway, all the experimental and their features were captured by theory, which made us which kind of resolved the puzzle for this anomalous feature at the second order, at the second harmonic of the cyclotron resonance. So let me just show you finally the movie of how this effect is happening. So I'm showing you the magneto absorption as a function of cyclotron frequency. And again, as I said before, at small frequencies below the gap, you have just the plasmonic mode. And then as you come to this regime of flat plasmonic dispersion, you get this coalescence of two modes of these two kind of intersection of from your dispersion. You reach this flat region, and then you have a giant absorption of electromagnetic radiation. With that, I would like to sum up with the third story, and would like you to take home a few messages that if you have a small device with sharp contacts, near field effects are very important in these devices, and you can have the cyclotron resonance overtones facilitated by the sort of magneto absorption caused by Bernstein modes in graphene. I mean, if you were to think it's why else this can be interesting and important, is because you kind of engineer on demand this strong magneto absorption. You engineer on demand the strong light matter interaction, and the only thing which you have to have is, again, it's very natural. You need to have a flat plasmonic or flat some kind of collective mode in your system, and you need to be able to absorb this the radiation through this mode. And to this end, you just need to ensure that those harmonics exist in your system from the scattered light. You can do it by having very sharp gold contact or needle connected to your graphene channel. All right. So with that, I think I've told you pretty much everything I wanted to discuss today. And if any of you are interested in exploring these directions further, please get in touch. Here are my contacts. Thank you very much for your attention.
Thank you very much, Denis, for this wonderful talk and for telling us about these fascinating results. So now we have some time for questions. So if you have a question, please feel free to write it in the chat or raise your hand. Yes, Peter?
Yeah, I was wondering, so actually on this slide that you have out now, so you were saying that you could visualize this with a scanning near field optical microscope, this how to say, these scattering patterns. I guess you could also then do like if the dispersion was not isotropic, you could probably, I guess you could kind of map the band structure from the angular dependence.
The band structure of you mean the dispersion of plasmons?
Yeah, basically.
Right. Let me think. So in principle, yes. So in principle, if you were to do this kind of experiment using near field microscopy, then again, by changing the frequency of incident radiation and changing the magnetic field, you should be able to visualize and reconstruct this, these modes for sure. Yeah. But the challenge so far, to the best of my knowledge, there exists only one system in the world, maybe I'm wrong, where near field scanning near field microscopy coexist with ultra low temperatures and strong magnetic fields. So you need to have these three components, and to the best of my knowledge, there's only one system. I think in was it Stony Brook, somewhere by the New York. It is there, yeah. But like usually people would have near field technique without magnetic field. Yeah.
Yeah. Okay. Thanks.
Yeah, maybe I can ask one question. So, Denis, in these experiments, the magnetic field is out of plane, right? So
right.
What would happen if there's also an in-plane component of the magnetic field? Is there some effect for the in-plane component, or only the out-of-plane matters?
Right. This is interesting because in-plane would not alter the plasmon dispersion, but it would introduce some Zeeman splitting for the band structure for the bands in graphene, right? And then you can think about some kind of two subsystems with spin ups and spin downs sitting in your systems, and maybe but they will not. I think they would not know much about each other because they interact through the Coulomb interaction, right? So they would not care which kind of spins would that. So that in that case, you would, I think, smear out the electronic dispersion. So you would have two subsystems with two kind of densities of electrons, right? But they would not be coupled. So I think this would not have much of an effect on this system. I guess this would be my guess. Yeah.
All right, I see. Thank you so much. So there's one question by Fabian. Fabian, please go ahead.
Yes, I have a question to a first part where you suggested these kind of graphene-based terahertz detectors. The general principle, as I understand, is very similar to a photoconductive antenna. So what do you think is what's the advantage of a graphene-based detector compared to a classical photoconductive antenna?
Right. So in photoconductive antenna, what happens is the following: you have a biased semiconductor or gallium arsenide or usually it's a gallium arsenide two-terminal device connected to an antenna, and then what happens is that you bias it. There is no current until you shine a strong femtosecond pulse on your gallium arsenide heterostructure, and then you induce photoconductivity by exciting charge carriers in the conduction band, and there is a very strong transient current, right, flowing through your device, which gives rise to the emission of terahertz radiation, or vice versa. If you have incident terahertz radiation in the biased device, once you shine once you shine a femtosecond light, you have a transient current which you can convert to electrical signal, right? So this is a very different regime of operation because all of these are based on the femtosecond excitations of non-conductive gapped semiconductors. In our case, we're dealing with the conductive system where we have essentially a typical standard field effect transistor in which we can have a plasmon mode sitting between the source and drain terminals. So the system is already conductive, and the rectification principle is not based on the enhancement of the photoconductivity, but it's built on the nonlinearity. Well, it's based on the nonlinearity of the transistor characteristics. So it's a different rectification mechanisms in those two cases, in the photoconductive antenna and in our devices.
Okay, thanks.
All right, so I think that there are no further questions from the audience. So in that case, I would suggest that we can stop the colloquium here. But first of all, thank you so much, Denis, for this really wonderful talk. It was really inspiring to hear about these very nice results on graphene plasmonics. And thank you, everybody, for coming to the colloquium. And
thank you very much.
Yeah, thank you. And see you next time. Have a nice day.